Armed with this notion, I'm now ready to tackle this thing called the Rice expression. As I mentioned, the Rice expression is a nice way that's typically developed in high school but works just fine in college for us to be able to fill in the boxes of everything that's going on in a chemical reaction that's proceeding toward equilibrium. If we think about what's going on, I can actually create a picture that looks like this. Let's just look at this thing. Spend a lot of time looking at this. There's my mass action equation right there, my general chemical reaction. A plus B going to make C and D. Right. Now, let's think about what's going on in a chemical reaction. There are basically two times in a chemical reaction that I'm interested in. I'm interested in the time when I'm not at equilibrium, and I'm interested in the time when I am at equilibrium. Well, what I can do is write down a nice little array right here that says for this reaction, A plus B goes to make C plus D, there's my amount which happens not at equilibrium. Oftentimes it's when we're starting a reaction. And I've got a certain concentration of A, B, C, and D at that non-equilibrium time. As I said, most often it's when you start an experiment. So, I'm going to go get me about a mole of A and a half a mole of B and a little bit of C and no D, and I'm going to mix them together in a liter of water. At that moment, you've created the starting A, B, C, and D concentrations. And then you say, ready, set, go! And the reaction happens. And it falls down the hill. If Q is less than K, it's falling down the hill to the right. If Q is greater than K, it's falling down the hill to the left. But when it's all said and done, guess what? It has gotten to a place where I have equilibrium amounts of A, B, C, and D. I have my starting non-equilibrium amounts. I have my ending equilibrium amounts. Notice how I write the form for this. Notice that capital letter C for the starting analytical concentration, and the lowercase is simply the subscript for the particular kind of material. And then in brackets is my equilibrium amount. That bracket always refers to the amount at equilibrium. What's interesting is I can simply say, wow, when I'm not at equilibrium, if I were to ratio the stuff on the right to the stuff on the left, that would be equal to Q. But when I am at equilibrium, if I ratio the stuff in brackets on the right to the stuff on the left, that's going to be equal to K. So here's this Rice expression, reaction, the initial conditions, and the equilibrium conditions, and that's what I'm trying to fill in.